So we started the recording for today's class. I hope this would work well. Sincerely hope so. I'm going to shut off this book backup and sync. It takes a lot of memory space. And find out that stuff.
স্যার আমাদের সিলেবাস শেষ করতে কত মান্থ লাগবে?
That's a very difficult question. Well, usually I start the classes from July. I finish by December. So usual time frame is 6 months. I hope the same for you.
স্যার আমাদের চ্যাপ্টার 1 টা তো প্রায় শেষ, রাইট?
আজকে শেষ হয়ে যাবে না স্যার?
হোপফুলি আমি আশা করতেছি আজকে খানিকটা ডিসকাশন করার পর মনে হয় আমরা ওয়ার্কশিটে কিছু প্রবলেম অ্যাট লিস্ট এমসিকিউ প্রবলেম সো দ্যাট ইউ ক্যান পিক আপ সাম স্পেসিফিক স্টার্ট করতে পারবো। আই রিয়েলি লুক ফরওয়ার্ড টু ইট। আচ্ছা, লাস্ট ক্লাসে তোমাদেরকে আমি যেটা দেখাচ্ছিলাম সেটা ছিল হচ্ছে যে হাউ ক্যান উই ক্যালকুলেট দ্য আনসার্টেনিটি ফর quantities which have an operator attached with them. For example, we discussed about the different index which handles with sign ratio, and I also told you that if we have other ratios involved, you need to apply your basic understanding of mathematics so that you can actually understand that how the value can be maximized. So if you have a fraction, you need to have a large value for the numerator, a small value for the denominator, so on and so forth. So that was the pretty much the end point of the discussion for how can we give multiple type of achieve the calculation requirement for multiple type of uncertainty calculation. And then other part that I actually skipped through the process before when I come to the uncertainty calculation is this part, that how do we handle with precision and accuracy? What do I mean by that? But before getting into that, I'm gonna first talk with this table. Many of you know this table from your O levels. You know what this table means mostly. 10 to the power 0 is 1, which is unit, and then below this thing we have two more short form. 10 to the power minus 1 in deci, and 10 to the power minus 2 is centi. And these are the two parts that we still use. And for example, 1 deciliter cube is 1 liter. So 1 decimeter cube is 1 liter. That is 1000 ml is 1 deciliter cube. Liter is still used in some part of your chemistry for the mostly like the molar calculation or something like that. And then so we still use these two prefixes of 10. And other than that, we have the tens power for the lower version, which is 10 to the minus 3 is milli, micro, nano, pico, and then we can have all the way up to femto. So these are all having a negative increment of 3. So 10 to the minus 3 milli, 10 to the minus 6 micro, nano, pico, and femto. What you really need to understand that all of these prefixes are using small letter for their prefix symbol. Milli is small m, micro is a bit Greek or Latin symbol. I don't know which one it is. I always confuse this up. Nano is small m, pico is small p, femto small f. In the upper bound, we have in order of magnitude of increment of 10 to the power 3. We have kilo, mega, giga. This is 369, and then we have tera. You just know what is a terabyte because of the computer memory amount. And then we have peta. Peta is 10 to the power 15. Above peta, we still have exa, and we also have, I think, peta for exa for aro ase, but for your syllabus volume, you don't need that much. You have up to 10 to the power 15 volume. This table is good enough for your syllabus requirements. So it's important that you understand and remember this symbol. For example, if in any case they give you that our device is having a kinetic energy of 1 capital T joule, so you should understand that this is 1 terajoule. Or if they give you that 110.3 p meter, so it would mean that 10 to the power 10.3 petameter. So it is 10 to the power 10.3, 10 to the power 15 meters. So it's important that you remember the symbol. You don't have to give a very hard effort towards memorizing this table. what I recommend that you know that this table is with you. You can also Google or look it up on the Wikipedia to have a much bigger version of this whole table on the lower side and also the upper side. And any single time you come across some symbol that you cannot make sense of, just get back to the table, have a look at it, and use that for your purpose. Try to learn the symbol meaning as you use them. You don't have to memorize them like the tables or something like that. I don't recommend this. Then we have this thing. Let me just discuss this part, and then I'm gonna take you through the reading. The first thing that we have that we can have in any type of measurement, we can have two basic type of error. One is what we call random error. The other one is that what we call systematic error. The idea of these two type of error is very important. For the time, you just don't start reading through the volume. I'm going to minimize this so that you don't read through the volume. I'm going to talk to you about it, and then I'm going to read it to you. So just listen. If you have your booklet over here, also please don't look at it for the time being. Just try to listen. Random error is a type of error which can arbitrarily give you a bit more for some of your measurement for the same quantity with the same instrument. Sometimes can give a bit less for the same measurement. A random error is basically the type of measurement, the error in a measurement which can have your value arbitrarily or randomly more or less. It has the ability to shift your value in higher direction or also in the lower direction. Either of them can happen, and you cannot have a good control on this. So this can be in both ways. So typically, typically random error is associated with human error. So any type of measurement, whenever a person is doing some sort of measurement, that human error always comes in for the random error effect. This is the most common source of random error. However, devices can also do random error, but it is actually quite rare, and you need to have some really predefined and very rare case. I'm going to give you an example which should make sense with you. But one of the example for human-based random error is the most common type of error that we always handle is the time measurement. If we human beings, any of us, is trying to measure any amount of time using a digital stopwatch, we always have random error of our creation time affecting that measurement, and we cannot get rid of it. But we have to know how can we handle this type of error. That's the important bit. However, devices tend not to do random error. I'm going to tell you an idea for device-based random error after I discuss the part of the systematic error so that it can make better sense to all of you. So what we have over here, why isn't all table? Okay, random error, which makes the reading deviate on both sides of the actual value, more and / or less. For example, human error in measurement of length, error happening due to parallax, human error while measurement time, error due to reaction time. So pretty much everything that is mentioned over here are relevant to human error. If you wonder that, well, if we have parallax mentioned over here, what is this human error in measurement of length? I mean, why these two things are mentioned differently? Let me tell you this thing. Sometimes human beings can make a mess while measuring the meter scale and mess it up. Let me give you a very weird and not so common, but somewhat possible type of error value. Let me just find out the meter. Yes. Okay. So let's say this is a meter rule. A person is trying to measure some length of an object. So as you can see over here, this meter rule has 100 divisions over here. So every division shows you this is 10, and this is actually 100 centimeter gives you 1 meter, right? 1000.
Yes, sir.
Yes, sir.
So each of these length over here that they're showing right over here is actually 1 centimeter, I believe. 10 centimeter, 20, 30, 40, 50, 60. Yeah, these are all centimeter. So the smaller division over here is centimeter, which is not the ideal case for our typical meter rule. But maybe this can be a better image. Yeah, this is a better image. Here they have mentioned the writings are all in stock image. So all of these marks that we have over here represent the meter rule value. Now, what you have to understand that this is a meter rule which has a significantly labeled zero error, or something that we call the dead space, because on the left of the zero you can see there are 5 divisions available over here. This is given in some cases for accuracy's sake. Some meter will have some dead space, marked dead space, just because in some measurement it might be necessary. However, if we disregard the type of human error, I mean, the weird type of human error can be, let's say an object is supposed to be, let's say 14.6. Let's say an object comes to the length, if whenever you have aligned one side to the 0 side, the other side comes aligned with the 14.6 mark. Now, they see centimeter written over here, but they forget about it. So they read 14.6 and they record that length 14.6 millimeter. It's an honest mistake, but it's a dumb mistake. It's not 14.6 millimeters, 14.6 centimeter. Then again, sometimes students tend to do always also this kind of mistake, that they see that the object is, let's say, up to 14, and then they're supposed to read 14 and 14.1, 14.2, 14.3, 14.4. They're supposed to read that way. But in some cases, pretty rare, but in some cases, students tend to do this 14, and then the first digit they read 15, 16, 17, 18, 19, 20. So up to 6 divisions after the 14 small digits, they keep on counting from 40 and they get 20. And just because they don't want to use their head, because they know that measuring the length is literally so easy, they simply write 20 centimeter. However, it was not 20 centimeter. They messed up their reading procedure. So these type of errors are what we call human error. These are random error. This can happen. This might not happen. If someone mess up their units, it can happen. If someone mess up their counting, it can happen. If someone mess up with parallax error, this can also happen. So that's why this bullet was given with a different, with the human error in measurement of length. That's basically the lack of judgment for that measurement. It's not very common, but what I need you to understand that it is possible to happen. That's all you need to consider. The next thing that we have, human error is also called personal error. That's also another name. Apart from human error, devices can also make random error. Example, I'm to pore বুঝাচ্ছি. Let's have a look at systematic error. Systematic error causes a reading to always deviate in one direction. That's the definition. Try to assimilate that. Systematic error causes readings to always deviate in one direction, always more or always less than the true value. Now, before I get into that, let me elaborate the idea of true value. True value of a measurement is something that is pre-known to us. For example, let's say in a laboratory, to check the capability of the students is to measure the length of, to measure the thickness of a certain steel plate. Let's say I have a certain steel plate, maybe the thickness of a basic stainless steel knife. So not the nail part where you have sharp. Let's say the very thin rectangular part. Let's say I have one kind of that steel plate which is uniform in thickness that I know for a fact, and I want the students to be able to measure the thickness of a of this metal sheet precisely. And because I have measured this a lot of times for the sake of my laboratory purposes, and I have made other students of other batches from, let's say, 5-6 years, a lot of students have measured this same specimen. So I have a round-up value of a statistical average of a huge amount of data, from which I know that what is the accurate thickness or acceptable accurate thickness of this specimen of steel piece, maybe up to 5 to 6 decimal places. That's the average value that I have. This kind of data is what we call the true value of a certain measurement. This can also be applicable for other objects. For example, let's say if you measure, what does that sound? Why set is doing such a big fuss about in my class?
VPN.
No, I don't have to use VPN. আমার ইসেটের লাইসেন্স শেষ হয়ে গেছে, লাইসেন্স কিনে আবার লাইসেন্স লাগাইতে হবে আমার। সো ইসেটের জন্য ঝামেলা করছে, আমি আনইনস্টল করতেছি না, বিকজ আনইনস্টল করলে আমার সিকিউরিটি আরো ড্রপ করবে। সো লাইসেন্স কিনে লাইসেন্স লাগাইতে হবে, এটার জন্য ঝামেলা করতেছে। ডিসরিগার্ড দ্যাট। ইসেটকে আমি অ্যাকচুয়ালি এখন স্টার্ট অফ করে দিলে there is possibility that আমার এই ল্যাপটপটা within 2 days মারা যাবে because by all the malware and the spyware and the other ransomware attack is possible. So disregard the problem for the time being. So let's get back to the point. Other examples of true value can be that you can have multiple values for a measured gravitational acceleration at a certain location. For example, like I said in the earlier class, that if you have
the statistical data of a lot of group of students over the years from multiple batches of students, O levels and A levels, and you have the value measured of G, and then you accumulate all those data, have an average. You can have a pretty much pure value of that exact gravitational acceleration of a certain location. You can actually have that, and you can consider that value to be the true value of G at that location. You can either do that, or you can actually buy some of the very precise instruments which you can buy online, and they will be delivered to your doorstep through some international delivery service. You can turn on that device, and that device can go ahead and do its own job and eventually give you an absolutely correct true value of G. That can be also done. So true value is a reference value for a certain certain quantity which we know to be exact and to be correct. That's what we mean by the word true value. Systematic error is a type of error that can deviate our measurement data only in one direction from the true value. So it will always make the value somewhat bigger or it will always make the value somewhat smaller. In most cases, systematic error is caused due to device error, or something that we call machine error. What is this word? Yeah, something like that. If there's an example of it, for example, zero error in screw gauge will always give slightly longer reading if it's a positive error, or slightly shorter reading if it's a negative error. That's why positive errors, whenever we subtract, that makes the actual reading somewhat smaller. So with the error, with the presence of a positive error, if it is not corrected, then we have that positive error present in the data, which makes the reading somewhat longer. So a meter rule that has positive error. Hold on just a second. I'm not all this. I'm just this class. Okay, she cut off. So positive error makes the reading somewhat bigger. So if you do not correct your data, connect your reading for positive error, all of your collected data will have some sort of will be somewhat bigger than what you're trying to measure. And similarly applicable for negative error. So systematic error is pretty much always happening from within the device, and in many cases, systematic error can be of the same value. For example, zero error is a constant value, so it would not actually give you different values of positive error. So if you have a positive error which you don't correct, all of your readings would be it would be bigger by the same amount, but that is not always the case for other type of measuring equipments. So there are certain type of systematic errors which can give you one type of error, always increase error, but the amount of increase in error can be decreasing or increasing, which are more likely to case work out for trigonometric case, which you are going to see more examples later on. One thing that I postponed in the earlier discussion is that how can a certain device error can give us a random error? Have a look at this example. Apart from human error, devices can also make random error. Usually, it's quite rare. For example, error while measuring volume using measuring cylinders on different days of the year can give a positive or negative error in reading depending on the temperature of the lab that day. Let me give you an idea. আসলাম ভাবি আমি ক্লাস নিচ্ছি, আমি একটু পরে কথা বলি। Okay, done. So let me give you let me get the image of বলে measuring cylinder. বলো আমার কথা শোনা যাচ্ছে?
Yes, sir.
বলো, yes sir.
Sir, can we say that human error is a subset of random error? Man, it's not equals to random error, right, sir?
No. Random error is the type of one of the two types of error. Human error attributes towards the most amount of random error. Let's say in all the experiment, in all the data that human beings could possibly do, let's say 95% or maybe 98% of all the random error is done due to human beings, and maybe 5 or 2% of the errors are done by devices. So random error is mostly done by human, but there are some few random error that can be also attributed from equipments. One of the examples which I'm trying to share right here. Can I get a higher resolution picture of these things?
Settings, search settings. No, not this one. কেমনে করে জানি হাই রেজলিউশন বাই করে মরে গিয়ে না tools size large. So this is a high resolution image. আচ্ছা এই জিনিসটা কোনো মতে আমারে ঠিকমতো ব্রাউজ করতে দিতেছে না, কারণ হচ্ছে যাও উপরে যাও 4147 by 4147. Okay. Why do I pick such a high definition image? Because I want to all of you to see something. Open image in your tab. Okay. Have a look. This is a bit. This drawing is from the front side. It's a bit tilted because they have, I think, done something with the alignment of the picture. You can see there is a thing mentioned over here, 20 degrees Celsius. Do you see that? Everyone, do you see it? 20 degrees Celsius is mentioned over here.
Yes, sir.
And also it says that plus or minus half milliliter. But you can see
Yes, sir.
that the smallest division that you can measure with this device is actually 1 millimeter. The reason they are considering that the measurement is 0.5 millimeter, because whenever you are going to have your reading anywhere in between, you're going to choose either the upper bound or the lower bound. So the maximum amount of error they are assuming that you could possibly do is actually half millimeter. So because your reading should not be more than half millimeter more or half millimeter less. If you choose the closest boundary, your reading can be minimum, maintained to be minimum within half millimeter for one observation. And and obviously, whenever we are using the measuring cylinder, if you're trying to measure the volume of a single object, we always take that one reading. But if you're trying to measure the volume of an object by the subtraction of two different water volumes, for example, if you first fill up the water volume over here, so let's say it is at some level, then you put in a solid object that submerges completely within the water and doesn't get absorbed, doesn't react. And then you may get a second reading, and then you take that second reading and do the subtraction. In that case, half and half is gonna add together to give plus minus 1 milliliter for the volume of the object. Each reading has an uncertainty of half milliliter, but if you are using two readings to get the value of a certain quantity measurement, then definitely it can add up 0.5 plus 0.5. You know this thing. We discussed this thing in the last class. But what I'm trying to consider over here, that there is a measure, there is a value shown over here that is 20 degrees Celsius. What is the significance of this temperature value? The idea of this temperature value is that this measuring cylinder has a fixed volume, fixed internal volume, and it is capable to measure that internal volume precisely at 20 degrees Celsius. The factory, the lab where this measuring cylinder was manufactured or it was calibrated, that factory was maintained at a perfect 20 degrees Celsius because temperature has a significant effect on object's volume. You have to understand that if we use this measuring cylinder in some other place or in a laboratory other than the manufacturing factory or the calibration lab, let's say I buy this measuring cylinder and I'm about to do an experiment. I can see that my measuring cylinder is 20 degrees Celsius. To make sure that I get the exact reading of some liquid, I should use this measuring cylinder at an environment where it is also 20 degrees Celsius. That way, I can get the actual true reading of volume of the object of the amount of liquid that I'm trying to measure. If the temperature of the room is somewhat bigger than 20 degrees Celsius, let's say I have to use this measuring cylinder in a hot temperature of let's say 50 degrees Celsius or maybe 60 degrees Celsius. It's pretty hot. You can understand that in that hot temperature, the measuring cylinder is going to expand in volume, which means that inside cross-sectional area is going to become larger. So the same amount of liquid is going to cover less height because your area is large. So the amount of liquid is going to cover less height. So in that case, at higher temperatures, you're going to get a smaller height reading, which means your measurement would be somewhat smaller than the actual volume. Do you understand my point?
Sir,
Yes.
is this because the cylinder will expand and occupy less height?
Exactly, precisely. Beautiful. That's exactly what's going to happen. And vice versa, if we have to use this measuring cylinder at a temperature of, let's say, less than 20 degrees Celsius, let's say 5 degrees Celsius or 10 degrees Celsius in a cold air weather,
then the cross-sectional area is going to become shrinked, is going to become smaller, and then the height of the liquid value should be higher than what it should be. Now, this is a type of equipment which has a significant dependency on the ambient temperature for which we are using it to measure the volume of a certain amount of liquid. Now, what is important that if you're in a geographic region, if your lab is located within a geographic region where the temperature of your lab room or the temperature of your ambient, let's say you're doing some measurement in a forest or maybe in a tropical forest, where in the midday the temperature can go really high above 20 degrees Celsius. Maybe at night the temperature can drop lower than 20 degrees Celsius. So if it's such, then you can have more readings at certain part of the day and less readings at certain part of the day. If it is not such that you have so much variation for day and night, if you have year-wise variation, let's say in the summer, the temperature of your geographic region where you are located, that is, let's say, above 20. So let's say the average temperature of your summer is about 25 degrees Celsius, and average temperature of your winter is, let's say, 8 degrees Celsius for your geographic regions. Certain year it can be vary a little bit because climate always is a bit changing factor. But it's, let's say, the average is those numbers. So it means that during the summer period, you're going to have a lower reading, which means you're going to have one type of random error. And in the winter, you're going to have another type of random error. The reason we are calling this error to be random, because same device is giving you two type of error, sometimes more than what it should read, sometimes less than what it should read. These two type of error for different time period of the day or maybe different time period of the year because of its dependence of temperature. So this is a type of example where a device might also be a source of random error. Not so common, but possible. Does it make sense?
Yes, sir.
Yes, sir.
Yes, sir.
Beautiful. So that's for the two type of error that we have. Here we have some important bits. These are pretty important for MCQ questions. It says that to avoid random error, we must do repeat and average. Honestly, repeat and average is pretty much the only weapon we have against repeat and average. The idea of repeat and average goes like this. If you are gonna try to measure a certain value with a human effort, and the idea is that if you measure that value 5 times, we assume that 2 of the readings are going to be on the plus side, 2 of the readings are going to be on the minus side, and 1 reading might as well be somewhere in the middle. So it's a statistical approximation. It's a guess. But for 5 reading, it might not be that easy to happen. So if you increase the number of readings, let's say if you go for 10 readings or 20 readings, or maybe if you go for 100 or 1,000 readings, then the approximation can become even more. I mean, whenever you're going for 100 readings, you can pretty much guess that more than 45 readings are going to be on the plus side, more than 45 readings are going to be on the minus side. The remaining 10 readings might have a bit of shift on either side. That might be a bit of random, but you can have an uniform distribution of multiple readings on both sides of plus and minus of the actual true value. So that's, so whenever you're going to average all of those numbers, you are going to you should pretty much land on the actual true value. That's the idea of repeat and average, that we tend to do the reading multiple times so that we make both type of error less or more, depending upon our measurement technique and the alertness of the experimenter. But ultimately, whenever we repeat and whenever we add them up and average, we can altogether minimize the error by compensating on both sides. That's the whole idea of repeat and average. Number 2 bullet says that to avoid systematic errors, we must check the instrument before use and correct each reading accordingly. So that's pretty much the only way to avoid systematic errors, that before you use the device, you should know what kind of systematic error the device might have. For example, a meter rule can have dead space. A micrometer screw gauge can have 0 errors. So if you have some other type of devices, for example, let's say, although it's a bit of a human error, but if you think for the mass, the top pen balance, kids, have you seen the top pen balance? Digital mass balance. You place an object on the steel plate and you get the reading and a digital value.
Yes.
That digital scale, it can actually give you, typically it can give you readings in 3 different units. It can give you reading in kg, it can give you reading in gram, it can also give you readings in pounds, lb. So if you mistakenly It's also a bit of a human error, but if you mistakenly choose, let's say, the pound option, and then you don't, then you forget to observe that option choice in the display. Rather, you put objects over here and record all the values, and you write them in kgs. Then you're always going to get a much wrong value. All of your values would be nearly 2.5 times smaller than what they should be, because you chose pound in the device, which you didn't observe. You're assuming that the device is giving you kg readings, but you forgot to observe that. So that can be also considered to be a systematic reading. And on the other hand, you can also say this is a bit of a human error, because human forgot to do the observation. Well, but then again, the human forgot to do the observation, but the device is continuously give you one type of errorful reading. That all the readings that you are gonna get, they're all gonna be either smaller than what they should be, or they're all gonna be somewhat bigger than what they should be if you mess up the unit choice. So all of those readings done by that person at that incident are gonna be having systematic error. But when another person come in and use and they mess up it in a different way, then it can be a mix up of random error and systematic error. Both that's it's a bit getting a bit complicated for a simple example. You really don't have to bother for that kind of complicated example. What I'm trying to tell you is that you have to know what kind of systematic error a device can have. I mean, you have to know the device inside out. That's the important bit. And before you use that device, you have to look for those error sources and have a measurement of those error sources. And each and every reading that you take, they should be corrected in accordance with the amount of error. If it's a positive zero, you subtract it. If it's a negative zero, you still subtract it, which ultimately gets added, but you get the point. So that's pretty much the only way to avoid systematic error. There is no other way. You repeat an average does not at all get rid of systematic error. Systematic error will always be present unless you manually correct it. Then we have this two topic, which is called precision and accuracy. Okay, these two terms in general life, in regular life, we consider them to be quite similar. But trust me on this one, they are not similar. They have individually different meaning for their purposes in physics. Precision means refers to how close multiple readings of the same measurement are. So, reading it, precision refers to how close multiple readings of the same measurement are, which means you are trying to measure one thing. You're going to measure it multiple times. You're going to record all of these individual readings. Now, in your head, they're supposed to be same, but if you are honest to your equipment and you are honest to your measurement, in many cases, they might not be the same. For example, let's say you're trying to measure the thickness of a glass block using a micrometer screw gauge. You are repeating that measurement in say 10 or 15 different places around the whole glass block. You should not get the exact same measurement, but logic tells you it's an uniform glass block. At least it looks to be a uniform glass block. The thickness should be same everywhere, but you shouldn't be getting the same reading every single place. So if you record all of this data, and then if you have a look at the spread out of this data, if the data are less spread out, I mean, if they're really clustered together, they're pretty close to each other, then we're gonna say that set of data is quite precise. So precision is not about a single data. Precision is the property of a group of data, whether that group of data, which all came from the measurement of a single quantity, if all of those data are really clustered close, if they are in between differences are pretty small, then we're gonna call them precise data. If they're really spread apart, I mean, they're going in all over the places, in that case, we're gonna call them less precise data. So that's why it says more, less, less. So if they are more close, they are more precise. If they are less close, they are less precise. Accuracy, on the other hand, accuracy can be applied for a single reading. Accuracy can be also applied for the average of a group of reading. So accuracy can be compared for a single value. If you are choosing any exact value, in that case, you have to consider whether that exact value, how much close that exact value is with the true value. Accuracy tells us that refers to how close the average of the readings and true value is. So you have to first of all know the true value of a certain thing, and then if the average of your group of data is close to that true value, then we can say that value to be quite accurate. If it is not so close, if it has a significant gap, the average of your cluster data is far apart from the true value that you know from earlier, then we are going to say that group of data is less accurate. So accuracy is about how close the average or a single data is with respect to the true value, and precision is about how closely clustered or how spread apart the values themselves are. A set of data can be precise, less precise, more accurate, more precise, less accurate, less precise, less accurate, more precise, more accurate. They can have all of these 4 different variations. We're going to see some examples how we can represent those kind of variations just after a while. Here it says a very important information. If you have your booklets already, you should star mark this information. In any experiment, low precision comes from high random or personal errors and vice versa. It means that if a person is less careful in doing the experiment, they are being careless and not paying good attention, doing a lot of parallax or doing random measurement error in every single places, then their experiment is going to have scattered data all over. So that is going to result in a less precise set of data, which represents more random error. And on the other hand, low accuracy means typically high systematic error. Low accuracy means that the total average of your data is significantly far away from the true value. Now that the whole data to be far away from the true value essentially requires that some data has always been far apart from the true value, which caused the entire calculated number to be far away from the projected true value. So if you're making some systematic error and you did not correct those systematic errors in the process of your calculation, then all of your combined result is going to be somewhat far apart from your true value. So systematic error typically is the reason for a low accuracy value and vice versa. So I'll say this again, that high precision data means less random error, and low precision means when the values are really scattered, which means high random error or high personal error. And for the systematic error, less systematic error means higher accurate reading, and more systematic error means less accurate reading, so far away distance from the true value. Here we have some example for the there are multiple ways to represent different levels of accuracy and precision in an experiment. So let's say here I have shown you some values. Let me tell you what these values are. Let's say for a 1 meter length of a simple pendulum, the time period for one oscillation is supposed to be 2.135 seconds. I did not write the unit over here. I should have written the unit over here, but I did not write the unit over here because I did not write the unit in all of these places. So I have only written it in this part. Let's say the true value for a 1 meter length of simple pendulum is supposed to be one oscillation to a time period is supposed to be 2.135 seconds. That I know as a true value. Let's say 3 different students are doing 3 different experiments and they come up with this set of data. So what the first one has 2.10, 2.11, 2.09, 2.13, 2.12, 2.08. These are the values that the first student gets by their repeat and average. Repeat and average means what? I mean, a student is never going to measure the oscillation duration for one oscillation. That's highly impractical. So they might observe at least 5 oscillations back and forth, and they're going to sync up their hand motion so that they can actually take a good measurement of the data. Or they can also choose to take 10 oscillations for a better accurate reading. So this student did their steps and they came up with, this student had these 6 set of reading for the same 1 meter length. So this is the first t value, second t value, third t value, like this. So you can see over here that the difference between the smallest and the highest value in all of these data sets. What is the smallest value of all these 6 numbers?
2.08.
2.0. Yeah, I agree it's 2.0. Does everyone see that 2.0 is the smallest number here? Everyone?
Yes, sir.
Okay. So if you try to find out the difference between the smallest and the highest value, this is one of the ways how can we actually find out whether the data is precise or not, to find out the difference between the smallest and the largest. So 2.0, if we find out the difference between 2.08 and 2. What is the other value? 2.08 and 2. And the biggest value is I think 2.13. Yeah. So if we find out the difference of these 2 terminal values, minimum and maximum, that difference is 0.05. So that's a pretty small amount of deviation. And the average of all of these numbers is coming up to be 2.10. 2.10. So I'd say these measurements are high precision because the deviation is quite small. And this number is actually quite close to this number. 2.10 and 2.135 can be considered to be quite close because it is carried up to first decimal place. So it's carried up to 1/10 of a second. The difference is coming up in the second decimal place. So which means this measurement is actually highly precise and also highly accurate. So this experiment was done by a careful candidate, and the equipment that the person were used were also carefully observed and carefully handled. I'm saying carefully handled because not to imply that the devices had very less systematic error. Whatever the systematic error that the devices might have had, the student knew how to take care of those. The student knew what measurements, what observations to take, how to balance those out so that ultimately our value come up within the necessary range. So this set of data can be said to be high precision and high accuracy. So it has low random error and low systematic error. I forgot to write this maybe. So, and then over here, we have some data of a second experiment. This one has values 1.98, 1.99, 1.90, 1.92, 1.95, and 1.92. Here, the difference between minimum and maximum is 0.09, slightly more than this, but we can still call them a highly precise set of data because it is only defined up at the second decimal place. So it is up to 1/10 of a second. It is pretty much correct. In the 1/100th of a second value, it is giving us a bit of a difference. So this set of data can be also said to be highly precise. However, the average of this number is 1.94, which is pretty far away from 2.135. So we're going to say this is a low accuracy set of data. We say that high precision, high accuracy, high precision, low accuracy. So it means low random error, possible systematic error. The reason I'm writing possible systematic error because this actually shows that all the data has been divided in one direction. That actually means systematic error. I shouldn't have written possible systematic error. This essentially represents a confirmed systematic error, but that systematic error might actually happen from some sort of error in that device, but also some sort of a wrong judgment of the person continuously making some wrong observation. That is also possible. But we are going to call them definitely highly systematic error. So possible shouldn't be here. It's a confirmed systematic error because all the data has shifted to one direction because the average of all the data is significantly smaller than the true value. We're going to say that this set of data is less accurate or low accuracy data. The third set of data is over here. We have a pretty hodgepodge set of data done this by this student. We have 1.60, 1.80, 1.90, 2.20, 2.20, and 2.50. So this one has pretty spread out data. And if we take all the differences over here, we have 0.90 amount of difference between the smallest and the highest data. So it's actually quite large because human reaction time is about 0.4 seconds. If you consider the start and the stop both, and if you divide them over 10 measurements, at least 10 oscillations, then your uncertainty should be 0.08. 0.08 is supposed to be the maximum value of your random error, but in this case the random error is showing up to be of 0.90 seconds, so it's not precise. However, if you do the average, it so happens that this value is 2.05. 2.05, if you take it into 3SF value, if you consider it over here, the difference between these two numbers are also quite less. I mean, the difference between 2.135 and 2.05 is only 0.80. So you're only having a difference in the second decimal place, which means this time period calculator is start up to the first 1/10 of a second. 1/10 of a second accurate correct measurement is actually considered to be pretty accurate. So somehow the student was lucky to get a accurate set of data, but the result of this experiment shows that this student was really callous and not careful in their readings, and they had their readings shooting up in every direction. But somewhat, they managed to get lucky enough so that their data eventually averaged out to give us a pretty accurate value. It can happen. So we say this is a high accuracy set value. We have low precision, so it is of high random error. So this is how we can judge a set of numbers to observe whether they're precise or accurate or both or none of them or one is precise or it's accurate or not precise or this kind of variations can happen. This is a judgment that we have to do just by looking at this set of data. You might wonder, one of the questions that should definitely pop in your head is that how do we know that how much range of data is, I mean, how much difference between the smallest and the highest can be considered to be precise, and beyond what number should we consider it to be not precise. And also, if you want to consider something to be accurate, I mean, how close does it have to be accurate, or how close, I mean, to what amount of distance, or to what amount of difference from the average and the true value should we consider it to be less accurate? Well, rule of thumb is that you don't really have to take that decision at your level. You don't have to take the decision at your level, but there is a certain mathematical procedure which you're going to learn in your lab procedure in question number 2, the very last thing, that they ask you to measure the percentage difference of two different values that you're going to measure, and they ask you to make some comment about this. The reason in many of these questions of lab paper number question number 2, they ask you to measure the percentage difference, because the idea is that your uncertainty of the measured value should be less or at least equal to percentage difference. I mean, your percentage difference of measuring the same quantity by two different methods should not be more than the uncertainty of the whole thing. I mean, uncertainty of a derived quantity basically gives us the idea, percentage uncertainty, I'm sorry. Percentage uncertainty of a derived quantity basically gives us the idea how much maximum error of percentage could this procedure of experiment have. So let's say if a certain derived data is supposed to have, let's say, because of the limitation of the equipment, is supposed to have an uncertainty of percentage uncertainty of, let's say, 15%. Let's say, well, it means that we have calculated the fractional uncertainty of all the relevant quantities that we measured, then we put them in the equation and eventually found out a percentage. It tells us that the percentage uncertainty of a certain derived quantity is 15%. It means the maximum error that you could possibly do if you mess up the equipment usage to its maximum, the maximum error you could have is 15%. Your devices limits your data to be errorful up to 15%. Now, if you are a good experimenter, your experimented result, I mean, by doing independent average, should be less than 15%. Because if you are doing a significant number of repetition and eventually doing the average, you are expecting to compensate all of your data towards the center, to converge the value towards the center. That's the whole idea of average. So if your percentage difference, which is a measure of how worse your experiment was, if your percentage difference is more than 15%, it proves that you yourself introduced a certain amount of more error other than the 15% of systematic error or the percentage uncertainty you might have had because of your devices or instruments limitations. So let's say if the percentage difference is coming out to be, let's say, 20%, whereas your percentage uncertainty is only 15%, it means that you could not confine your experimental outcome within the 15% limitation that you should have had. Rather, your careless data collection or your uncareful data collection or your incapable data collection led up to an additional 5% of error to with the additional to the 15% systematic uncertainty that you might have had. So there is actually a method of this madness, not madness. I mean, there is a certain method of judging how much is to be considered to be the limit of precision or limit of accuracy. You, for your theoretical course, do not ever have to memorize these values, because in most cases you're going to be given multiple set of values where you have to judge that which one between two is more accurate, which one between two is more precise. So that should be very easily judgeable. In most cases, you don't have to choose which one can be said to be not precise and not accurate. You pretty much always have to choose between two or more. The one that is more precise, you just find out the difference of the maximum and the minimum for all the values. The one that has the minimum amount of spreading, that is the most precise value, and the one which has the average closest to the true value, it can be said to be the most accurate as well. We're going to see some example of this thing in our MCQ papers just after a while. So let me just go on to the next thing. This is actually a visual representation of accuracy representation. This actually represents a number line. Let's say this is a number line, where this long line is actually the true value of a certain measurement. Yes, I'm sorry, I just have to pick this call. So I'm pause recording. So consider these straight lines as some sort of a number line. which well, let's say 0 is somewhere on the left, which is not shown over here. The true value is represented by the long central line, and this small lines represents the experimental outcome of the raw value of a measurement. And if it so happens, they can be also the derived quantities or calculated value, but this one represents the true value. This one represents the individual measurement of a certain quantity. It can be if it's the length of a certain object, which is a direct measurement of a measuring equipment, we call it a raw value. But if it's the outcome of a certain amount of calculation, for example, if you're measuring the time period of a single calculation, you don't measure it by a single time. You actually take 10 oscillations and divide by 10 at least, and then you calculate the single time oscillation time period. That's a calculated quantity. So it can be also that. But here, the long line represents the true value, and the small lines represent the experimented value. Now, if it so happens that we have a distribution like this, we're going to call this set of data high accuracy and high precision. The reason I'm going to call high accuracy because the numbers are seen to be somewhat equally distributed on both sides. So if you take the average, all of these things, you can pretty much expect the average to fall exactly on the middle, and the values have a bit small gap between their smallest value and their highest value on the two sides. So that makes it high precision, high accuracy. This set of data can be said to have a low accuracy but high precision, because the values themselves are pretty close to each other, so it shows high precision, but their average would be somewhere at the middle, where this is the true value. So the average is actually pretty far apart, so the accuracy is missing. This can be said to be high accuracy because the average would be pretty much matching with the true value, but they are to be of low precision. This is the worst type of example. We have low accuracy and low precision. These four set of data can be also described in terms of random error and systematic error. This one represents low random error and low systematic error. This one represents low random error and high systematic error. This one represents high random error but low systematic error. This one represents high systematic error and high random error. So accuracy and precision are just opposite to the type of error. Precision is relevant to the random error, more or less, less more. More precision means less error, and vice versa. And accuracy is relevant to systematic error. More systematic error means low accuracy, and vice versa. হ্যাঁ, ইউসুফ বলো।
স্যার আমি অপশন সিটা স্যার বুঝতে পারছি না স্যার।
Option C হচ্ছে in the option C we have the individual experiment obtained values to are placing like over here, where the true value is over here on the number line. So if you average these values together, because you can see that they are pretty much evenly spread out on both sides of the true value. If you take all of these individual small numbers, small line numbers, and find out the numerical average, that average value would be pretty much close to the true value, because you have pretty much even spread out on both sides. That's why we call this set of data to be accurate, because their average would be quite closely matching with the true value. However, because the values themselves are quite spread out, I mean, the values are not really close within themselves. That's why they are not very precise.
Sir,
Yes.
বিচে এটা হাই প্রিসিশন কেমনে? ওটা তো মেইন লাইন থেকে অনেক দূরে না?
মেইন লাইন থেকে অনেক দূরে জিনিসটাকে আমরা কি দিয়ে ডিফাইন করি? Have a look at the definition. I mean, pretty far away from the true value is defined by which property? Have a look. Precision refers to how close multiple readings are. Accuracy refers to how close the average of the readings are. So if you consider this figure, these values themselves, are they pretty close to each other?
Yes, sir.
High precision. But if you find their average, will that average of this data, which should be somewhere in the middle, is this pretty close to the true value?
No, sir.
So low accuracy.
Okay, sir.
বুঝা গেছে?
জি স্যার, বুঝতে পারছি।
আচ্ছা। The third graphical way to represent this one is a bit somewhat slightly more difficult to understand. Let me elaborate how this graph was actually made. On the x-axis, we have the value, and on the y-axis, we have number of same readings repeated. Now, let me elaborate this in a certain way. So I'll try to draw it in the MS Paint. Let's say I don't have a right pad, so I'm going to draw with mouse. let's say you have a lot of different values. Let's say you are measuring a certain quantity, let's say 100 times. Let's understand this thing. You are trying to measure a certain quantity, let's say 100 times. You wonder, why would someone measure the value of certain so single value 100 times? Well, someone or by their own self might not, but let's say I'm trying to measure the actual value of gravitational acceleration g in my place of location, and I have, let's say, a student group of 100 people. I assign all of them equipment set in different part of the day, so or different part of the week, and I collect 100 set of data from 100 different students who have all done the same experiment, and I try to plot the value of g in a graph. Let's say on this axis I'm placing the different values of g, and on this axis I'm gonna place that how many times a single value was obtained by multiple students. Let's say this is the actual true value of g for my experiment location. Let's say this is 9.8163. So let's say this is the actual value that is for my lab location. This is the true value of my g that I should get. Many students might get 9.8, less than that. Many students might get more than that. So if I have a plotted value over here for multiple different values, so I have a scale over here. Each of these lines represents a specific value, let's say up to 1 decimal place or 2 SF values. So it's possible that some students might get this value by a certain number. Let's say out of the 100 measurements, maybe 2 students got this value. So I'm gonna mark this at 2. So this is gonna be one of my plotted points right over here. And then this, let's say this is another value. Let's say 10 students got this value. So I'm gonna have this at 10 mark, and this value was obtained by 10 students. So 10 students got this same reading. So I'm gonna get a plot plotted over here. So like this, I'm gonna place the frequency, the number of times the same value was obtained for multiple observation or for multiple experiments in a certain graph, and that graph should typically give us a graph like a hill kind of shape, which is somewhat bit like normal distribution. So that's the typical idea for the case of shift frequency. So on the y-axis we have the n represents the how many times a single value was repeatedly obtained for multiple measurements, and on the x-axis we have the actual values that what we are trying to get. So that's how these graphs were made. So if we have a look at this thing, if we have a graph that looks like this, let's say the dotted line in this case represents the true value line, and whereas this curve represents the plotted points joined with a base fit curve. If it so happens that this curve is actually quite thin, and the crest of this curve perfectly aligns with the true value, it means we have uniform distribution on both sides. So that gives us a pretty accurate set of reading. And because the values are really close to each other, I mean, you don't have values which are really far apart from the true value. Most of the values are really close to the true value. That's why you have such a thin and long curve. I mean, you had this number pretty for a significant long number of times. You have another close number repeated for a very big number of times, another very close for a very big number of times. So your actual spread of the data from the true value, the difference of multiple measured values from the true value was actually quite small. Most of your data, most of your 100 data, or maybe 1000 data, or no matter how many times you have, most of your data were pretty close to the true value. They are not exactly the true value, but most of them were pretty close. So that type of a distribution represents that we have high precision and high accuracy. So the way we need to judge this thing is that if this hill is a thin and tall hill, then it's high precision. I mean, for example, the shape over here and the shape over here, this type of shape represents high precision values. And the accuracy is judged whether the peak of this hill is perfectly aligned with the true value, because that alignment proves that the numerical average of all the data on left and right, left and right, left and right, the numerical average is gonna give you pretty much the same value of the true value. So the judgment of the shape, a thin curve gives you high precision, and the peak matching gives you high accuracy. So based upon that judgment, we can have 4 different variations over here. You should understand this is high precision and high accuracy. How would you describe this graph? This is not written over here. The other two are written, but how would you describe this graph? Is it precise or less precise?
High
Sir,
precision.
it's a highly precise but less accurate.
Beautiful. Perfectly stated. So this set of data is highly precise because they are really close to each other, but they are not accurate because the crest of this whole hill is not perfectly matching with the true value of the experiment. So this is high precision, low accuracy. I would like all of you who have collected your book to write this thing over here. High precision, low accuracy. Can লিখো, নিজেরা লিখে নাও। Then we have this idea, we have low precision and high accuracy. Low precision because the values are really spread out, but somewhat the peak of the plateau, this is not actually a very sharp hill. This is a sort of like a blunt hill, so I'm calling it a plateau. So somehow the crest of this curve is still matching with the true value. So we're still going to call it accurate because the average of all of this number should still give us the true value. So high accuracy, but low precision, and then the worst of all, low precision, low accuracy. So this is another way to represent a set of data in a graphical manner if we want to represent them in this way. These observations can show up in another way, which is shown up over here. Now, this is a pretty interesting graph. I'm going to give you a certain scenario for you to visualize. Let's say you have built a robot that is supposed to shoot an arrow or maybe a nerf gun, whatever.
Nerf gun, sir.
Nerf gun, yeah. Let's say it's supposed to shoot an arrow or a nerf gun to a certain target, And let's say you have placed your target bullseye at 10-meter distance from the arrow, or maybe 5-meter distance, whatever your distances are. Now, let's say you're going to shoot 20 arrows towards your target, and you're going to try to look at the distribution of all the individual hitting points. If it so happens that all of these arrowheads are pretty consistently around the bullseye, you can say that it is this robot is precise and highly accurate as well. However, if it so happens that the arrows are all coming up at in a close cluster, but they are really significantly far away from the bullseye, then they can be said to be highly precise, but not highly accurate, which means this one means that your machine is working perfectly. It is capable to shoot multiple arrows pretty much in the same location, but you need to realign the aiming mechanism. That realignment or systematic error adjustment would actually make this experiment successful. Whereas option 2C, high accuracy, low precision, means that your device is not well made. Every single time it shoots, it can shoot in random faraway points. It means your nuts and bolts or all the fastening mechanism, or maybe the material itself of the whole thing that you've chosen, maybe the plastic is too thin. So every single time it shoots the arrow, it flexes a little bit different times in different direction. So you have a device which is incapable to shoot in a single defined location, but the aim is pretty correct. That's why it is shooting all around the bullseye, but the distribution is pretty much uniform around the bullseye. So you can say that the arrow is aimed properly, which means it is quite accurate. However, the device itself is not working precisely because its aim is really not at where we want it, but it's all around the whole spectrum. And if that spread out happens in a really far away point, then the bullseye, I mean, I have a compare to these parts. These are the set of data that these are the set of data that are calling to be precise, but these are the set of data that are calling to be less precise. So it means that they are shooting apart as well, and they are also not aligned properly, which means this is representing low precision, low accuracy. You might wonder that why am I using the example for bullseye example? This bullseye example or the aiming example really helps to visualize this whole example very clearly. However, for the case of a mathematical approach, this same idea can be used for a two-dimensional graph. I mean, you need to understand that this thing that I just showed you over here, this is a one-dimensional representation. That here is a standard, here is the true value, and here are multiple other single values. So we are comparing the clusterness closeness of these values and also the average position of these values compared to a single standard. Whereas over here, we can consider this whole plane to have a y-axis on over here and a x-axis over here, and these positions can be used to represent the coordinates in a two-dimensional graph system where multiple different values are showing to be in multiple different places. So this shooting dot example can be also equally used to represent a two-dimensional data representation. That can be also pretty helpful for us.
Sir, একটা question ছিল।
Sure.
Sir, ওই যে সেকেন্ডটাতে স্যার, ওই যে সেইটা না স্যার, এটা নিচেরটা স্যার, ওই যে বুলসআইটাই স্যার, যে বিতে স্যার ইউ শোড দ্যাট it will build a robot or which will be aiming, তাই না স্যার? তো ওই পয়েন্টগুলোতে স্যার লাইক তার মানে রোবটের আর্মটাতে একটা সমস্যা আছে, লাইক ডিভাইস সিস্টেম্যাটিক এরর আছে, যেটার জন্য একটু রাইটে রিফ্লেক্টেড হচ্ছে।
Exactly, right and up. So the device is working pretty well. The device is aiming pretty much consistent, pretty much close to a single point, but you need to realign the aim so that you can get it at the correct point. Or exactly, or in other words, you need to readjust the systematic error of your system so that your values actually get close to the true value. That's another way to say the same thing.
Yes, sir.
Any other question? So yeah, we have the descriptions over here, high pitch and lower, high P, lower. So this is just all mentioned over here, and then the student actually write all of this over here for easy understanding. Anyway, it all works out just well. And then comes the uncertainty part. We actually went to the uncertainty part in our earlier classes, so I'm not gonna get into this. Let me just see if we have anything else showing up on the later part of this class note. Uncertainty measurement.
Sir, uncertainty definition take to apologize the range of values along which a value is supposed to lie.
I'm actually uncertainty formal definition bhule gechi.
It need apologize, sir. The range of values within which the true value is supposed to be like lie or be situated.
Actually, I wouldn't use the term range. I'll tell you why. Because let me just write and try to elaborate. If we are trying to talk about uncertainty, let's say if I write a certain number, let's say 92.4 plus or minus 0.1. Okay, I'd say this is the uncertainty. It's not essentially all the values from 92.3 all the way up to 92.5. Well, these are the two range values between which the value could possibly lie. But we do not call this whole range to be uncertain. We rather call this value to be uncertainty. So one of the things is, if I was trying to define this within this term, I'm not sure if this is the actual textbook definition. I'm going to look up the textbook definition or Wikipedia definition right now. But if I was trying to explain this thing, depending upon the lectures and understanding that we have gone so far, I would write it in this manner, that uncertainty is the maximum possible variation a certain measured quantity might have. Do you understand my point? Because whenever I use the term variation, it automatically implies more or less.
Sir, repeat
I would not recommend you write this. You can write this for your own understanding, but I'm not sure if that's the actual definition. I'm going to look up the definition in a while, but you can write this for your own understanding. Uncertainty is the maximum possible deviation a certain value can possibly have from its measured value. পড়ে দেখো, see if it makes sense.
জি স্যার, লিখছি স্যার, বুঝছি স্যার, it makes sense.
Let me just look it up on Wikipedia a little bit. World's most informative website without ads. Uncertainty refers to epistemic institutions involving imperfect or unknown information. It applies to predictions of future events, to physical measurements that are already made, or to the unknown. Uncertainty arises in partially observable or stochastic environments, okay, as well as due to ignorance, indolence, or both. Indolence means laziness, okay. It arises in any number of fields, including insurance, philosophy, physics, statistics, economics, finance, psychology, sociology, engineering, meteorology, ecology, and information science. Okay, that's a mouthful definition. Uncertainty definition for A levels. That should give us a more precise. The smallest change in the quantity being measured that gives a recognizable change in reading. The uncertainty of a measurement is the bounds in which the accurate value can be. Hassan, you just said this thing to me, right?
Sir, আমি রেঞ্জটা বলছিলাম।
Okay, range is basically the bounds. Bounds and range pretty much mean the same thing.
জি স্যার, নোটসেও লেখা ছিল স্যার এটা, যেটা দিছিলেন স্যার।
তাহলে সেটাও হইতে পারে। I actually forgot the actual textbook definition of it. I know what it means, but I forgot the actual definition. So let's have a look at the actual definition for within this. So
স্যার আমাদের কি কোনো নতুন বই দিবে স্যার এবার ফিজিক্সের জন্য, কোন সাবজেক্টের জন্য তা আসতেছে স্যার, এই যে 5th এডিশন নাকি or something?
দিতে পারে। নতুন বইতে ফিজিক্সটা নতুন হবে না, জাস্ট কন্টেন্ট গুলো একটু নতুন হতে পারে বা নতুন ভাবে রিঅ্যারেঞ্জ হতে পারে। That's the best can happen.
But it's coming to Bangladesh, right? Actually, chances are there.
You can wait to buy a book, or you can just go use the notes for the time being to do your worksheets for your understanding. And if you know the new book is made available, you can choose to buy it. I really don't hold a hard and fast rule that when you should buy a book or whether you should buy a book at all or not. But having a book beside your class notes, and class notes is the most precise and what can I say, the what can I say?
Easy to understand.
No. I'm not going to say that. It is the most gist part of the content that enables you to solve problems. I mean, the part that, it is the tool that helps you solve. Without the box, without the cash memo, without the warranty information, none of this is available to you. You just have the tool to solve your problem. That's what the notes are. That's what all of my notes are. It only enables you to solve problem. That's it. That's how I look at it. I mean, the book essentially gives you more information, background, and a more holistic understanding towards how things work.
If about the sir level and অনেক বড় বই শেষ করা যায় না স্যার।
Well, you're not supposed to read it as something that you should aim to remember word by word. You should read it just to make an idea generation, and certain part of the book should feel interesting to you, which you can mark for later reading because it interests you. Some of the part might seem difficult, which you might feel important, but it's difficult for you to understand or difficult for you to remember at times, but you feel that it's important. So you can also mark those parts that you design a record for me, but I tend to have a bit of difficulty, so I need to revise them more often. So one part is your interest part, and the part is the difficult part. These are the two parts that you need to focus more on a future steps. Other parts which you just read through is basically sort of like filler. So it just fills in the information between every bit of important. For example, let's say Isaac Newton was sitting under an apple tree, apple falls down the tree, then he thinks about why did the apple fall through the tree. He came out with the idea of gravitation. Now, gravitation is, now comes the actual physics. So all of those earlier 4 or 5 sentences is just a bit of historical background, which you don't need to read ever. But knowing it gives you a bit of a conclusion. If that makes sense.
Yes, sir.
I don't see the definition of uncertainty over here. They have just directly started through the notes, and okay, I think it's a bit later. We have errors, random errors, precision, resolution, accuracy. Repeatability is the original experiment can read the with the same experiment method that get the same results is repeatable. Okay, this one is redone by different personnel, different things, and it's reproducible. Yes, these two things are two very fundamental requirement for a scientific hypothesis to become a theory. A hypothesis is something that is proposed which is not yet proven. A theory is something that is proposed and proven time and time. So the theory of relativity is a proven thing. Whereas even when we used to be a student, I mean, back in 2000, 2001, I mean, within the end of the 20th century, let's say, I mean, Avogadro's hypothesis was a hypothesis for a really long time because no one could actually count that number. So it was physically impossible to count that many molecules within 1 mole of substance. So the number that Avogadro proposed was considered to be a hypothesis for a very long time. It was say Avogadro's hypothesis. But what the scientists found out that even if it cannot be counted physically, the number of particles within 1 mole, all the calculations and all the temperature variations, pressure variations, volume variation that can actually lead up from the calculation of Avogadro's constant utilization, they all proved to be consistent. And that's when Avogadro's hypothesis was considered to be Avogadro's theory, and Avogadro's number was considered to be an Avogadro's constant. So that's a what can I say, upgradation or significant promotion from a lower level idea to a universally accepted rule of thumb. This is pretty good stuff. The uncertainty of a measurement is the bounds in which the values can be expected to lie. It's the same definition. Uncertainty of a measurement is the bounds in which the accurate value can be expected to lie. The true value could be within 80 to 20. So yeah, Hassan, what you just said is correct. What I just said is actually less correct. I stand corrected here. What you said that this range is what you're going to call the uncertainty. This is actually the way it is defined within a syllabus, not essentially this number. I was going to say this is the uncertainty. This range is actually what the uncertainty is.
Yes, sir.
I'm sorry. What you said was absolutely correct. So disregard my explanation. It is actually the range within which the true value can lie, should lie.
Yes, sir. The smallest stat করে দিব, the smallest possible value.
I wouldn't
Now
say
this are
smallest, uncertainty, the number that we write after the plus or minus, this actually gives you the maximum upper and lower bound variation. So whenever we say the smallest, that smallest part is actually the smallest fraction the device can measure. For example, if I go into this PDF, I can give you this thing. I mean, resolution, have a look at this idea. The smallest change in the quantity being measured that gives a recognizable change in reading. For example, in the meter rule, the resolution is 1 millimeter. In the case of a vernier calipers, which has 20 divisions in the vernier scale, the resolution is 0.05 millimeter. For the case of a micrometer screw gauge, the resolution is 0.01 millimeter. It is the smallest variation that you can measure, or the amount of measurement that makes a recognizable change in the reading. It means if you're trying to measure an object or two different objects, which are, let's say, in their true property, they are, let's say, 0.001 millimeter longer or shorter. Measuring them by a meter rule wouldn't give you any different effect, because a meter rule is incapable of measuring that small difference. So even বুঝা গেছে?
Yes, sir.
এটা রেফারেন্স টু ওরা স্মলেস্ট পার্টটা বলছিল।
Yes, sir. It's clear now, sir.
Beautiful. Any other question, anyone? No. So let's try to solve some problem. We have 11 or a bit more than 11 minutes. So where is the MCQ paper? This is the MCQ paper.
Sir, একটা question ছিল স্যার।
বলো।
স্যার ওই যে আনসার্টেনটি যে কোয়েশ্চেন গুলো স্যার কোয়েশ্চেন পেপার এগুলোর জন্য স্যার অনেক প্রবলেমস করতে হয়, ওইটা কি ইয়েতে মানে অনেক রাফ ওয়ার্ক করতে হবে, এটা কি আমি কি পেপারে করতে পারবো?
আচ্ছা, হ্যাঁ হ্যাঁ ডেফিনেটলি এই কোশ্চেন পেপার গুলো অ্যাকচুয়ালি আমি অনেক 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 স্কুইজ করছি মানে হচ্ছে মনে করো অ্যাকচুয়াল কোশ্চেন পেপারে এই যে কোশ্চেন নাম্বার 9 এই পুরোটুকু মনে করো হাফ একটা পেজে ছিল। এই পুরো কোশ্চেনটা ছিল হচ্ছে ওয়ার্ড একটা ওয়ার্ড, এই সবগুলো ইউনিট ছিল হচ্ছে একটার পর একটা। দেয়ার ওয়াজ necessary কি বলে লাইন স্পেসিং, and maybe beyond the line spacing you had about 2 or 3 lines gap, then came another question. I concised the view of all of these questions just to make the worksheets thin, because back then I didn't have a plan to actually make them into a bundle and give them out as a bundle, which I am doing right now. But if I had planned it back then, I wouldn't have done this work. So you can definitely do all of your rough work in a different piece of paper. But what I highly recommend, if you are doing it in a loose paper, keep them stapled or along with your question paper, so that later if you have to take some reference, you can have a look at this calculation if you ever need it. Or if you can maintain a single khata for it, single Excel book, then you just put the date and worksheet number and page number, and then slowly start doing by numbers, so that you can actually also, I mean, my point is that wherever you do the calculation, if not utterly impossible, try to keep track of it.
স্যার এই এমসিকিউ গুলোর আনসার কোথায়, মানে কোটা দেখবো কিভাবে?
আচ্ছা, তোমাদেরকে আনসার বুকলেট দেয়নি?
P2 তো পাইছি লাল সাথে মিক্স করানো, কিন্তু এমসিকিউ এর আনসার তো খুঁজে পাইতেছি না এই বুকলেটে।
আচ্ছা, এমসিকিউ আনসার বুক তাহলে তোমাদেরকে দেওয়া হয় না। এমসিকিউ আনসার বুকলেট আমি তোমাদেরকে এখনই দিয়ে দিচ্ছি, কারণ এখানে মনে হয় এমসিকিউ আনসার বুকলেট দেওয়া হয় নাই, as far as I understand। দেওয়া হয়েছে কি এখানে?
কালেক্ট করা যাবে স্যার?
হ্যাঁ,
কালেক্ট করা যাবে স্যার লালমাটিয়া থেকে?
তুমি প্রিন্টার কালেক্ট করতে হয়েছে 12 পেজ পিডিএফ। আমি মামুনকে বলে রাখতে পারি, দাঁড়াও আমি এখনই তোমাদেরকে দিয়ে দিতেছি। আমি কি তোমাদের এখন দিতে পারবো? এখানে কি আছে? এখানে তো নাই, আছে হচ্ছে আমার বাসার পিসিতে। আচ্ছা শোনো, এটা আমি ইভেন্চুয়ালি আমার চিরাঙের বাসায় যাওয়ার পর তারপর পিসি থেকে তোমাদের শেয়ার দিতে পারবো। মানে এই ল্যাপটপে ওই ডকুমেন্টেশনটা নাই, আর মেবি আছে।
জি স্যার, ট্রাই করতে থাকি, পরে মিলাবো না স্যার।
না, ট্রাই করতে থাকি পরে মিলাবো না। এই সিস্টেমে তুমি অ্যাকচুয়ালি এমসিকিউ করতে পারবে না, কারণ এমসিকিউ রিকোয়ার্স এ কন্টিনিউয়াস feedback mechanism. And that's how I understand it. Does it get to my messenger or someone else's messenger? Please, my messenger. Yes, my messenger. Hold up. I'm pretty sure I shared it with the earlier batch. So if I get into their messenger group and look in the shared files, I might find this. Okay, I mean, at this point, actually, can pause the recording. Okay. One of the part that I actually forgot to discuss with you is the unit conversion of multiple different direct quantities. This is one of the very important part of your first chapter for the AS syllabus. Let me show you what it means. There are basically 7 base quantities: length, mass, time, temperature, current, luminosity, and the amount of substance. Out of these 7 base quantities, you are gonna use 6 of them. To be honest, more or less in physics AS level, you are going to use only 5 of them. You are going to use length, mass, time, temperature, and current. In your AS, you don't have temperature either. Luminosity intensity is nowhere in your entire A-level syllabus, not even included in your A2 syllabus. However, in the chapter of the new astronomy, now we have the application of luminosity intensity. So we're going to deal with luminosity intensity in the chapter of astronomy. Is going to be a part of there. The luminosity intensity, standard candle, everything goes around this unit candela. Anyway, other than these 7 base quantities, everything else are direct quantities: area, volume, density, specific capacity, specific gravity, repetitive index, blah 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 blah, whatever you name it. One of the important bit that you have to be able to do is to convert a direct quantity into its base unit expressions. And this can take some significant amount of practice and significant amount of take care. Let me show you what it means. For example, let's say এখানে কি এই ধরনের কোনো এক্সাম্পল করে দেওয়া আছে, এখানে একটা কোনো এক্সাম্পল করে দেওয়া নেই। সো আমি এখানে করি, এখানে করতে গেলে তো মোটামুটি আমার হাওয়া বাইর হয়ে যাবে, কারণ অনেকদিন মাউসে লিখি না। But I'll try anyway. Let's say I'm going to give you a direct quantity of, let's say, power. Power unit key.
Sir, what?
What?
Watt, sir.
What?
WATT.
আচ্ছা, পাওয়ার ইউনিট হচ্ছে ওয়াট। এখন আমরা বললাম যে এই the question is that we have to convert the watt into its base units. So how do you do that? To be able to do that, you have to remember all of the individual defining equation, important bit. You have to remember all the defining equation of those quantities so that you can slowly work your way down the line. Let me show you. Power is defined by what? Work per time or energy per time. So 1 watt or watt can be written as joule per second. What is joule? Per second is already is a base quantity, so we don't have to bother about this. We just have to put it
Force
down.
into displacement, joule, sir.
Exactly. Joule is the unit of work done, which comes from force into displacement, which means joule can be rewritten as Newton meter multiplied by second inverse 1. Meter is a base quantity, so we don't have to bother about that. So what we left is the Newton meter. What is Newton? What is
kgms minus 2, sir.
Exactly. Newton is force. F equals to ma. So Newton can be rewritten as kg meter per second square. So that's the Newton, and then you pull the rest of this thing right over here, multiplied by meter second inverse 1. আমি কিন্তু মাউস দিয়ে লিখতেছি, ওই জন্য লেখার অবস্থা এত খারাপ। বুঝতে না পারলে আমাকে জিজ্ঞেস করো, I'll help you understand it. So if we now combine all the powers, this is kg meter square per second cube. এই হচ্ছে ওয়াটের বেস ইউনিট কনভার্সন। এই কনভার্সন গুলো করতে পারতে হবে, এমসিকিউ তো আসে, পেপার টুতেও আসে। পেপার টুতে আসলে পুরোটা করে দেখাতে হয়, এমসিকিউ তো আসলে তোমাদেরকে জাস্ট রাফ ওয়ার্ক জায়গায় করতে হবে, করে তোমাকে অ্যাকুরেট কারেক্ট আনসারটা বাই করতে হবে। Unless you remember or you have difficulty remembering the defining equation for a certain quantity, this can prove to be a bit more confusing or time consuming as well. The most difficult of all of those direct quantities that you might ever have to come across, in my opinion, is resistance. At this point, I'm going to ask all of you to take, let's say, 2-3 minutes to give me the SI base quantity conversion of resistance, ohm. Try to convert ohm into SI base quantity, or I can keep this as a homework for Tuesday. I'll give this as a homework for Tuesday. I want all of you to try to convert ohm into base quantity, base unit in conversion. বুঝছো কি বলছি?
স্যার এখন করতে পারলে কি এখন করে দিতে পারবো?
Well, you can do this, and you can send the picture to me personally in the messenger. I'll have a look. I'll tell you yes or no, just that. But I'll show you the solution next class to everyone. If you really want to do this right now, I appreciate it, and you just send it to me personally, not in the public chat. I want everyone to have their own efforts. So this is the most difficult, in my opinion, for all the quantities that you might have to come across. So far, I understand, but there can be a lot of different quantities you might have to do. For example, volt is also a thing. Volt is actually joule per coulomb. So if you know, so volt is joule per coulomb. Joule per coulomb. This is volt. So let me give you a line over here. Volt is joule per coulomb now, -1. So joule can be rewritten as this whole formation that we have. I mean, this whole thing: Newton meter, kg meter per second into meter, and coulomb is actually ampere second. So here it would come as ampere second whole to the power -1. So that thing is gonna come out and initially get multiplied with the whole joule thingy, and you can get the whole expression, something like that. Now, another thing that is important, that I just showed you what volt looks like, and if you remember that ohm is given by resistance is given by V by I. So volt per current gives you resistance. So I'm not going to tell you anymore. I think I told you. Anyway, that's also another important part. I just remembered about this part just by looking.
স্যার গান পাঠাই দিব।
একটু পরে ক্লাসে শেষ করে নিই। So just because I was looking at this part, that how can the both sides of this equation in terms of the base units. So you have to be able to do this thing, that pressure equals to rho g h. So প্রেসারের ফুল বেজ ইউনিট কনভার্সন কি হবে, ডেনসিটির বেজ ইউনিট কনভার্সন কি হবে, জি কি হবে, এইচ কি হবে, সেটা তোমাদেরকে দেখে এখান থেকে জাজ করে প্রপারলি সিলেক্ট করতে পারতে হবে। আচ্ছা, হচ্ছে এখানে আরো অনেক কিছু আছে হাবিজাবি, এগুলো তোমরা ট্রাই করতে পারো। আমি নেক্সট ক্লাসে এখান থেকে তোমাদের কিছু এমসিকিউ সলভ করাতে পারি, অথবা হচ্ছে আমি বেছে গেছে কিছু এমসিকিউ সলভ করাবো। আর কিছু এমসিকিউ আছে যেগুলো আমি সলভ করানোর দরকার মনে করি, সেগুলো ডেফিনেটলি সলভ করাবো। আর হচ্ছে before I actually close today's class, I'd like to take your attention to the very last page of this worksheet.
Sir,
Not this one. মানে পেপার 2 এর লাস্ট পেজ, পেপার 2 ওয়ার্কশিটের লাস্ট পেজটা দেখো তো সবাই।
স্যার ওই যে বিভিন্ন অ্যাপ্রক্সিমেশন দেওয়ার একটা এমসিকিউ শীট দেওয়া।
Exactly. Please have a look at that paper. For those who haven't gone through the whole thing. পেপার 2 ওয়ার্কশিটের লাস্ট পেজটা একটু দেখো। I'm going to turn it over as well. হ্যাঁ, ইউসুফ কি যেন বলতেছিলাম।
স্যার আমরা কি এগুলো কি করে স্যার স্ক্যান করে পাঠিয়ে দিব স্যার আপনাকে?
No, you're going to have it with you. I'm going to discuss with you, and you should be keeping up with the discussion. If you really want me to have them checked, your worksheets checked, I mean, if you really feel that this necessary, I can arrange it with some of my ex-students who are willing and free and can put down the effort, who are in Dhaka, and they can do it through my office. So you don't have to know the process. You just have to submit the name. They will check it and then they'll return back to you. But for most part, you have to know what you are doing, taking help from my lectures, my discussions, and also the mark schemes and examination reports are also at your disposal. So you should know what you are doing and how much mark are you gonna get for a certain amount of answer, because you know how the marking is done so far. If you don't, I'll help you understand that as well, because that's the important bit. If you know how you're gonna be marked, you would be able to answer it properly as well. Do you understand what I'm saying?
স্যার আরেকটা কোশ্চেন ছিল স্যার।
এক মিনিট, ইউসুফ বুঝছো কি বলছে?
Yes sir.
আচ্ছা,
And sir, the last paper you just told us to check, it is this stupid questions in AS that require memorizing or smart guess.
yes,
Is it-
is that page.
Sir, are they really stupid, or I mean,
Have a look at them. Just have a look at them. These are only compiled from I mean, this doesn't have all the pages. This only has up to 2013 or 2014, the years that I compiled. I have just given them here as a simple example. Have a look at this thing. Make a reasonable estimate of the following quantities. Mass of an apple. How do you make a reasonable estimate for the mass of an apple? And more than that, why is it important that you should have a capability to make a reasonable estimate of an apple? Why should they ask you this question in a physics course? Here's the reason. Being able to do mathematical calculation with the help of formula and everything is one thing. Having an understanding of the physical quantities towards the real world is something that is also a very important, additionally required thing. So you need to be able to understand that 1 kg of substance, I mean, you understand 1 Newton equals to 1 kg meter per second square, that's okay. But how much is 1 kg? I mean, do your head weigh 1 kg? Do your whole body weigh 1 kg? Do the whole earth weigh 1 kg? How much is 1 kg? You have to understand, have a physical understanding for how much is 1 kg. For example, here they've given the mass of an apple is, they have given a huge, an unrealistically large range. But try to understand what I mean. If you have ever bought a kg of apple, you should, how many apples usually make 1 kg? How many of you have any idea about
4
this?
স্যার 10 বা
চারটা।
ছোট হলো, অনেক ছোট হলো।
ওকে, একদম ছোট লাল যেগুলো আছে ওগুলো 10টা হতে পারে, আর হচ্ছে সবুজ আপেল যদি তুমি নাও ওটা 4টা
এগুলো 5টা হয় স্যার।
ম্যাক্সিমাম 6টা, যদি
5টা
একটু বেশি ছোটগুলো হয়, ঠিক আছে? মানে এভারেজ 5টা আপেল হলে মোটামুটি 1 কেজি হয়। তখন তার মানে হচ্ছে টিপিক্যালি একটা আপেলের মাস হচ্ছে 200 গ্রাম about, right? Have a look that they have given an unrealistically large range. They have given allow 50 gram to 500 gram. It means if you consider an apple to have a mass of 50 gram, you're gonna require 20 apples to make 1 kg, which is like boroyer shoman, or maybe boroyer thekeo choto. If you consider an apple to be of 500 gram, which is also quite unrealistic, you're gonna have 2 making 1 kilogram. I haven't seen apple that big ever. But they have allowed this much big range, because students who are capable to guess within this range can be considered, according to say, to have some realistic idea about how the apples are. Although I find this range to be also pretty much ridiculous, but they have been liberal at this answer, so that many of the students can get it. But if some student actually gave answers outside this range, you really have to consider that these people don't have any idea about how much is 1 kilo or what is an apple. Either
Sir,
of
একটা
these
question.
are very
প্লে
unclear.
গ্রুপ করে নাই
না এখন maybe they have eaten apple in juice from all of their life. Maybe they have seen milk coming out of a fridge all of their life. So where does the milk come from? Not from a cow, it comes from a fridge or from milkman. You can never guess that level of understanding of people towards the world from the regular life experience unless you really check it. Did you get the example of the milk example?
ইয়েস স্যার
জি স্যার, স্যার একটা এক্সাম্পল আছে স্যার, ওই যে 1D তে স্যার, বুঝছেন, ওই যে ভলিউম অফ অ্যান অ্যাডাল্ট হেড, স্যার এটা কিভাবে বুঝবো? ইটস লাইক আই ক্যান অনলি চিন্তা করতে পারি ইন টার্মস অফ দ্য অ্যাডাল্ট হেড।
এসব কি কোশ্চেন
That's my point. I mean, the speed of sound in air, that should be some part of your web chapter, so you should know this thing. Density of air at room temperature and pressure, this is also a variable that you should know from your sound chapter, air pressure thingy. The mass of a protractor, how on earth, if you would you ever have an idea of how much should be a mass of a protractor? This is how you should have. If you have handled actual lab equipments, if you have ever handled actual lab equipments, you might have some idea how much a protractor weighs. Do you get my point? Because in many of your
Yes.
experiments, you're gonna measure the mass of a 6-inch scale. In some of your experiments, actually, you're gonna be measuring the protractor of a mass of a protractor. There are certain experiments where you're gonna require to measure that. Even if you don't measure that, I mean, if you just feel the mass of a protractor, how much does it weigh in terms of gram? You need to have some sort of idea for that. You can see over here, they have given a pretty large range, 5 gram to 50 gram. A protractor usually weighs about 18 grams, typically, the typical plastic protractors that we have, if I'm not mistaken. I hope I'm not mistaken. But anyway, they have given a period. Anyway, I'm not talking about question number 1D. The first time, I mean, when I actually came across these questions, well, first time teaching the students the AS syllabus, I was really bothered by these questions. Like, what is this? I mean, these are just 4 questions in the paper 2, and then other 2 or 3 questions in the MCQ paper are only there to steal away the mark of the students. I mean, this really doesn't make sense. That's how I felt. But then it occurred to me that these are the questions which actually check the understanding relevance of the students to the regular world. So these are pretty important questions. So the way I saw question number 1D was like this. I did not have any idea how much my volume or the head of a per person's volume. So I consider my head to be standard. And what I did, I took a regular long meter rule. I'm going to show this to you. I'm going to turn on my video. You able to see me?
ইয়েস স্যার
জি স্যার, দেখা যাচ্ছে।
Yes, sir.
I have a
বন্ধ করা যাবে, sir?
light behind my back. I'm gonna try to.
Okay, sir. আচ্ছা, স্ক্রিন শেয়ারটা কি বন্ধ করা যাবে, স্যার?
So this is
Yes,
what I
sir.
did. Actually, I have in my hand one of the lab meter rules, but your typical meter rules that typical rulers that you're gonna take to your lab exam are gonna be of 12 inches. So I'm gonna be using up to 12-inch mark over here, or about 30 centimeter mark over here. So this is what I did. I held. I'm gonna put my nail on the 30 centimeter mark right here. So right over here. So this is what I did when I first came across this question, is that I'm gonna try to measure the circumference of my forehead, around this forehead. So I place it pretty much by feel of my head at the center of my forehead, just like that, just by the feel, and then I wrapped it around. So just like that, I wrapped it around, and this was my approximate endpoint. And then I place the ruler at the endpoint, and then I wrap it around once again up over here. So this is my measurement over here, which is about 24. So the total circumference of my head is 30 plus 24 centimeter circumference. Now
Yes.
I'm considering my head to be almost a sphere. Now that's just an approximation that I'm doing. Approximation is allowed in all of these cases, because all of these values make estimates of the following. So 30 plus 24 is 54 centimeter. Considering 54 centimeter as a circumference, the radius of my head is gonna be how much? Divided by 2 pi. Can someone do that?
54 divided by 2 pi. 8.6 আছে।
Okay, something there. Cube that. Do 4 by 3 pi r cube. So cube into 4 by 3 into pi.
ওইটা কিউব করার পর কি করতে বলছিলেন?
4 by 3 into pi. Volume করতেছি।
Sir, 2.7 into 10 to the power 3.
So I'm gonna write that. Actually, আমার আরো বড় হওয়ার কথা তো। তাহলে আমি মেজারমেন্টটা ভুল করছি। আমার মাথার ভলিউম অলমোস্ট এই 5 into 10 to the power 3 সেন্টিমিটার মতো আসে। Anyway, but you get my point. This is how I solve the problem, and then I felt pretty good that my answer was within the range. Now, a person having 2 into 10 to the power 3 centimeter cube head is gonna be like the size of a tennis ball. Unlikely. Even kids have heads bigger than tennis ball, and because this is adult person, and 9 into 10 to the power 3 centimeter cube is pretty much the size of a basketball. Regular human being do not have the head the size of a basketball. So it's the guess that you have to understand that how many centimeter cubes is of what size for a spherical shape. So these are the kind of questions that you have to handle. These questions might feel annoying. In some cases, there might be the difference between getting an A or an A star, or an A and a B. But these are the questions which are important for you. So you have to be able to deal with that. Unless and there is no hard and fast rule that what these questions might actually entail in, but in many cases the questions come repeated. So you might actually find this question that there is one of this question over here. Where is that thing? What is the reasonable estimate for the average kinetic energy of an athlete during a 100-meter race that takes 10 seconds? So this question actually showed up in a lot of cases. And then over this similar question over here, an Olympic athlete of mass 80 kg completes in a 100-meter race. What is the best estimate of his mean kinetic energy? So if you can guess the mean kinetic energy, you can actually write that answer over here. So this kind of questions, many of these questions actually do get repeated a lot of times. So maybe you get lucky. Maybe out of these 4 questions, you might get 2 of them from the previous years. Even if you get 2 of them,
right?
exactly, you have to predict, but your predict has to be within reasonable range. That's the important thing. It has to be within reasonable range. You cannot make unreasonable. Yes, that's the whole point of these estimations. So এই কোশ্চেন গুলো একটু মডারেশন দিও তোমাদেরকে, এই কোশ্চেন গুলো প্র্যাকটিস করবা। আর আমার এই 2 পেজে শুধু 2013 পর্যন্ত কম্পাইল করা আছে, so you might as well look from that, from 2014 all the way up to the most recent papers and find out all of those other information. If someone can assign, some of you can make a compilation of those questions like in this manner and be willing to share it as a free PDF material for everyone else of your group or maybe for the whole world. Be my guest, be everyone's guest. God bless you. For that, and Jazakallah khair for that. I am not doing that because I want all of you to do your own homework to get your good results.
Okay, sir. Ji, sir.
Someone has written something in the chat window. So I should have, oh yeah, sure, no problem. So yeah, that's enough for today's class. I'm going to stop the recording and try to upload it from this laptop. I'm going to see whether it actually works out from this laptop, and I'll see you all on Tuesday. Thank you very much. Assalamu alaikum. Good night.
Sir, something homework this one, like your MCQ.
Try as much as you can at your own convenience.
Okay, sir.
Whatever you can feel like. It's only one day in between.
Okay, sir.